Hello friends, so far we have been looking into different laws of thermodynamics. So we began with the first law of thermodynamics that helped us understand or describe the static state of a system. So if we begin with a system that is stable and we introduce some changes so that the system moves to another stable state. So we have the initial static system and a final static system. So in the first law of thermodynamics, we were able to rather introduce a thermodynamic function to describe this static state of the system. Secondly, one way of looking into the first law of thermodynamics is it helps us rather account for the input that we feed into the system, the output that the system renders, and also the change exhibited by the system. So that is essentially what the expression that is associated with the first law of thermodynamics helps us understand. The input that is fed into the system, the output that is rendered by the system, and the change associated with it. So it achieves a right energy balance. Now, one critical aspect of the first law of thermodynamics is this first law of thermodynamics, even though it was rather postulated after the second law, the first law of thermodynamics rather essentially it encapsulates the fundamental foundation of the whole thermodynamics. The whole subject of thermodynamics is essentially captured in the first law. The reason is primarily because the first law of thermodynamics in a single expression, it relates both heat exchange and work done, which is nothing but the essential foundation of the thermodynamics. So therefore it is referred to as the first law of thermodynamics. So now you know why, even though this law was discovered or this law was postulated after other laws, the reason this is referred to as the first law of thermodynamics is because it essentially gives us a framework wherein we have an expression that relates both heat exchange and work done. So even though the first law has its own advantages or it has its own application, the first law of thermodynamics rather was largely restricted to the static system. So we wanted to move away from the static system. We wanted to consider the dynamic system, the system that is continually exhibiting a change, or when we observe it is exhibiting a change. So for that, we introduced a thermodynamic variable to describe the dynamic system. And based on the thermodynamic variable, we were able to arrive at different thermodynamic functions. So we considered different combinations of thermodynamic variables and we were able to arrive at a set of thermodynamic functions, and these functions helped us in describing a dynamic system that is exhibiting a change in state. So this dynamic system can exhibit a reversible change or an irreversible change. The second law of thermodynamics, it helped us describe or differentiate the reversible change from an irreversible change. It gave us appropriate criteria to distinguish one change from another. The third law of thermodynamics helped us helps us in making one of the variable that was introduced in the second law of thermodynamics more accessible. So we have first law that presents us with the framework of thermodynamics. We have second law that helps us describe the dynamic state of a system, that helps us describe any change in the state, any change that we observe in the physical world. So any change in the physical world that comes with its own characteristic change in the variables, we are through appropriate choice of the functions, through appropriate different relations that we have seen, we will be able to describe thermodynamically that change in the system. And the third law of thermodynamics ensures that all the variables, all the thermodynamic variables that we have introduced to describe the change in the state of the system are accessible. Even the entropy is accessible to us. So these are rather some takeaway points on all these three different laws of thermodynamics. Now from this lecture onwards, we will be rather exclusively focusing on the material aspect of it. So how this thermodynamics, which has so far been largely generalized. So we have introduced certain material concept whenever it was necessary, but largely so far our discussions were generalized. So from this lecture onwards, we will be exclusively attempting to relate the concepts that we have learned, the generalized concepts we have learned thus far, to the materials, and see how well we can understand the changes that the materials exhibit, the changes that we observe in a material. So in order to do that, it is rather important for us to get familiarized with one critical terminology or one pivotal terminology. Now, if you could recollect, when we were discussing the operation of the heat engine, maybe in the framework of Carnot cycle, or other ways as well. When we consider the operation of the heat engine is a form of an engine that rather gains or takes the heat as an input and transforms it into work. Now, in the framework of Carnot cycle, we saw that this heat, when we feed into the heat engine, it was not directly the transfer of heat. We had another system that was made to be in contact with our heat engine, and this contact helped the heat transfer. So let me repeat, when we consider the heat engine in the framework of Carnot cycle, even though fundamental understanding of the heat engine is that you supply in heat and it transforms it into work, this heat transfer did not happen on its own. The heat transfer, again in the framework of thermodynamics, was ensured by another system. So we had a system that was at a temperature higher than that of heat engine. So let us say T high. You have your heat engine, and this heat engine was at a lower temperature, and when you brought these two in contact with each other, there was a heat transfer. So whatever change that heat engine brought about, or whatever output the heat engine gave, was because of this contact that was established between this another system, quote unquote, and its contact between this and other system and the heat engine. So this system, we refer to it as reservoir. The reason we refer to it as reservoir, because after bringing the heat engine in contact with the reservoir, despite the transfer of heat, the temperature of the reservoir did not change. So essentially what we have done is, we have fed the heat into the heat engine, not just by heating the heat engine up, but by keeping or ensuring that this heat engine is in contact with the high temperature reservoir. So what essentially allowed for the heat transfer is the temperature difference between the heat engine and the reservoir is what ensured that there is a transfer of heat into the heat engine, and this heat engine, this transfer of heat, is what is ultimately responsible for the work done by the heat engine. So there are two processes. The first process is the transfer of heat. So when you consider what governed this transfer of heat, it is the contact between the heat engine and the reservoir, and it's just not the contact, it is the temperature difference between the heat engine and the reservoir. Now when you consider, so it is the heat transfer that acts as the input for heat engine, and this input is translated into the output of work. So we will consider these two steps. So when you consider what is responsible for the heat transfer, then the answer is the temperature difference between the reservoir and the heat engine. So it is, so when we consider when we want to rather describe this transfer of heat, or what drives, what governs, what dictates the transfer of heat, it is the temperature difference. So the driving force for the transfer of heat is the temperature difference, and this driving force is what is responsible for the transfer of heat, and this transfer of heat is what is responsible for the work done. So if you consider, if you remove the middleman here, what essentially is the driving force for the work done in this combination of reservoir and the heat engine is the temperature difference. So what essentially drives the operation of the heat engine is in the first place is the temperature difference. Now even though this particular example may be specific to the Carnot cycle or heat engine, if you consider the simplistic example of placing a ball of water in a freezer, what essentially happens is there exhibits, so you are not doing anything to remove the heat. What essentially you are doing is you are exposing this bowl of water to an environment, to a condition which has a temperature. So this is an environment which has a temperature that is significantly lower than the temperature of the ball. So when you want to freeze a ball of water, you are placing this ball of water into a freezer, and the freezer is nothing but an environment wherein the temperature is significantly lower than that of the bowl of water. So essentially, because of this temperature difference, the heat is removed from the bowl of water. So when the heat is removed from the bowl of water, the temperature within the bowl of water decreases. So you have a freezer, you place in the bowl of water. Because of the temperature difference, because of the lower temperature of the freezer, the heat is rather being removed from the bowl of water. Now here it is the freezer that acts as the reservoir, because despite the heat being removed from the water and being fed into the freezer, there is no significant change in the temperature of the freezer. So here the freezer acts as a reservoir. So after the heat is being removed from the bowl of water, the temperature of the bowl of water decreases and ultimately the bowl of water freezes. So this is the chain of event that we observe while observing a freezing or a simplistic change of the state of the change in the state of the water. So you have established a difference in the temperature, and this difference in the temperature brings about a heat exchange, and this heat exchange introduces a change within the bowl of water within our desired system, and this ultimately brings about a change in state. So essentially, again, what here we observe is the driving force again is the temperature difference. The reason we are considering these examples is primarily because we need to understand when we are describing the change in the state of the system, particularly with respect to a given material, we need to first identify the driving force for the change in the state of the system. Often these driving force can be related to a thermodynamic function or a thermodynamic variable. So in both these cases, the driving force, even though can be attributed or can be talked about or can be discussed in terms of heat exchange, primarily the driving force here in both these cases are the temperature difference. The simpler we are able to, or in the more simpler way we are able to express these driving forces, the more easily we will be able to relate or understand our phase transformation. So when we are considering a material and its change in states, it is required of us to understand what is the principal driving force that governs the change in the state of this system. Now, secondly, if we see a system like a system that is rather a composite, meaning it comprises of a solid and let's say a gas. So it comprises of a combination, is a composite system that comprises of solid and gas. Now you are feeding in, or you are raising the temperature of this entire composite system. Now when you raise the temperature of entire composite system, the solid rather it expands at the expense of the gas. So the solid, it expands at the expense of the gas. So the volume of the solid will be increased at the expense of the gas. So gas, assuming that gas is compressible. So in this case, there are two different pressures. So because of the increase in temperature, the pressure of the gas is increased and the pressure of the solid is also increased. So if you go into the microscopic state of the system, essentially you are increasing the kinetic energy of the atoms that constitute the solid and the gas, and this increase in the kinetic energy of the atoms that constitute the solid and the gas, it increases the pressure of the gas and the solid. Now, because there is a difference between the pressure that is experienced by the solid and the gas, you observe the volume of the solid is increasing at the expense of the gas. So you observe a noticeable increase in only one of these phases. So you have two, solid and gas, in a given system. You are exposing both these phases to a similar condition, but one of these phases experiences a noticeable change while at the expense of the other. This is because the one has gained a more pressure when compared to the other. Now in this case, the phase change, the volumetric change, is primarily because, or it is driven by, the difference in the pressure. So here in the initial cases, we saw that the change in the state of the system was driven by the difference in temperature, and here the change in the state of the system is driven by the difference in pressure. Now if you consider the difference in pressure and the difference in temperature, what essentially we mean by difference in temperature and pressure is that when you consider the pressure in the solid, it is different from the pressure in the gas. So the pressure in the solid, it is rather higher than the pressure in the gas, and that is the reason why you see the expansion of solid at the expense of gas. And similarly, when you consider say a bowl of water in a freezer, so this is assuming that this is a bowl of water and this is a freezer, the driving force is the temperature of the freezer is much less than the temperature of the bowl of water. Now the reason we are able to rather talk about the pressure of the solid and the pressure of the liquid, the temperature of the freezer and the temperature of the bowl of water, is because we have considered a specific example. Now when you consider a generalized framework, so it is because we have considered the specific example, we are able to talk about solid, gas and freezer, bowl of water. If we want to consider a generalized example, then we need to have a generalized way of representing this difference in the variables that dictate the driving force. So when you consider a generalized, or when you want to consider the generalized example, one way of doing it is considering the spatial position of or within a given system. So what we essentially see in both these cases is when the spatial positions vary, meaning when you move the position of your estimation of temperature or your estimation of pressure, when you move spatially within the system, be it in this system or be it in this system. So here you have a bowl of water and that is surrounded by freezer. Now when you measure the temperature across the different positions within the system, you observe that there is a temperature difference. So the best way of describing the driving force in a generalized manner, in a specific manner, we can talk about the pressure in solid, the pressure in gas, or the temperature within the bowl of water or the freezer. So that is the rather a specific way, a rather restrictive way of discussing about the difference in the variable that dictate the driving force. Now the generalized way, if you want to do it, we can do it by considering the difference in these variables according to their spatial positions. Now if you consider a one-dimensional system and a one-dimensional system, meaning if you consider a line, so this is just the one dimension, so just the x dimension, and you are measuring the temperature at each of these points, and you notice that as you move along this direction, so this is the x direction, and you notice that as you move along this direction, the temperature rather increases. So this is your x-axis and this is your temperature, it rather increases. So we can consider such a temperature change within each of these systems. So it is possible for us, irrespective of the system, it is possible for us to arrive at such a plot for the given system wherein there is a difference in the temperature. So a generalized way of representing a difference in a thermodynamic variable would be considering its difference depending on its spatial position. So that is what is represented in 1D here. Now if we want to numerically represent this change in the spatial position, it is nothing but the change in the temperature with respect to the position along the x-axis. Now this is again for one-dimensional case, and it can be used. So it can, this expression, this change in the temperature with respect to the x-axis can be appropriately expressed to describe the temperature difference within this system or any other system. So generalized way of representing the difference in the variable would be considering the variable, the difference in the variable with respect to the spatial position. So here it is for one dimension. Now if we want to consider it for all the three dimensions, then we have to include x-axis, y-axis and the z-axis, and this is what we refer to as the gradient. So gradient of a given variable, so instead of temperature let us assume a variable. So the gradient of any variable will help us understand the difference in that variable given within a system which would act as the driving force for the transformation. Here it is the difference in the pressure that acted as the driving force for the change in the volume of the solid at the expense of gas. Here it is the difference in the temperature that ultimately helped us achieve a phase change. So instead of expressing these two driving forces, the difference in the pressure and difference in the temperature, in terms of or in a specific manner that is rather restricted to each of these systems, a generalized way of representing it would be the gradient of those specific thermodynamic variable. So the driving force in most cases for a change in the state of a material can be expressed using the gradient of a specific thermodynamic variable. This gradient of a specific thermodynamic variable. Now, having said that, it is possible for us to go beyond our simplistic consideration into a system wherein you have mass transfer. So far what we have considered or what we have looked into is a system wherein the change is largely due to the difference in temperature or difference in pressure. So it is possible for us to also consider an open system wherein the change is because of the mass transfer. Then in that case, what we need to introduce would be chemical potential, which we saw in our earlier discussion. But for now, we will restrict ourselves to rather a one component closed system, meaning we will restrict ourselves to homogeneous system or system that is largely made up of only one component. So when I say one component, what I mean by that is a chemical component. So one chemical component, it could be an atom, ion, or a molecule. So it could be a pure element, a pure metal, or it could also be rather a ceramic that comprises of only one form of molecules that build that builds up the entire ceramic or the entire material. Or it can be, like we saw, an ice cube or a ball of water that purely comprises of just H2O molecules. So that is what we will be considering in this lecture. That is a component or a material that is made up of largely a single component. To make our discussion easier, like we have done in our previous lectures, wherein we begin with a simplistic consideration and we build on it, let us restrict ourselves to a unary system, meaning we are considering a system we are considering a system that comprises of only one form of atoms or one form of ions or one form of molecules. There are only one form of chemical component that constitute the system that we will be considering in this lecture. Now, if we consider the change in the state of such a system, or if we are considering such a system that is exhibiting a temperature difference, then in order to understand what changes can that particular system exhibit when the temperature changes, we have looked into several functions that can help us. So we have several different functions that can help us in describing the change in the state of the system when the temperature is changing. Now, we saw, while considering these different thermodynamic functions, we saw that one function is often employed to describe the change in the state of the system, and rightfully so, or preferentially used to describe the change in the state of the system when that system is a material, and that is the Gibbs free energy. Now, one of the reason is that the Gibbs free energy rather helps us describe, or the dynamic variable associated with the Gibbs free energy are temperature and pressure, which is often what we change when we are considering or when we want to introduce a change in the state of a material. So often it is the temperature and pressure that we employ to bring about a change in the state of the material, and a thermodynamic function that directly relates to the change in the directly relates us to the description for the change in the state of the system when temperature and pressure changes is the Gibbs free energy. So the Gibbs free energy, let us use the Gibbs free energy in order to describe the change in the state of such a chemical or such a homogeneous unary system that comprises of only one component. Now when we do that, what we end up having is, we end up having the expression such as this, which is nothing but the canonical description of, or what is not, which is nothing but the expression that we considered for the Gibbs free energy. So it is the change in the Gibbs free energy as the temperature and the pressure changes. Now, assuming that it's only the temperature that is changed and the pressure is constant, the change in the Gibbs free energy with respect to temperature can be expressed in this form. So to be consistent, this expression can be written as, instead of dt, we can have not infinitesimal change in the temperature or pressure, but the overall change in the temperature and pressure. So it can be represented in this way. So what we have considered is, we have considered a single component system. That component, that system is experiencing a change with the change in the temperature, and we want to describe that change exhibited by the single component system. And for that, we employ the Gibbs free energy. And now we assume that the pressure during this change is constant, and we end up having this expression here. Now it is possible for us to plot the Gibbs free energy versus the temperature plot for this system. A single component system, we have this expression for the constant pressure condition, and based on this expression we will be able to plot the change in the, or at least graphically illustrate the change in the Gibbs free energy with respect to temperature. Now when you consider this expression, the change in the Gibbs free energy with respect to temperature, or when you consider what would be the nature of the change, we can understand from this expression that the infinitesimal change of the Gibbs free energy with respect to temperature will be negative S. So it will be minus S or negative entropy. So this means whatever illustration that we will be considering to represent the change in the Gibbs free energy with respect to temperature should have a negative slope which is equal to that of with the magnitude of which is equal to that of the entropy. So therefore, schematically, for a single component system and which is experiencing a change in the temperature at constant pressure, the corresponding change in the Gibbs free energy will be of this form. So again, this is a schematic representation, and the only the reason we have such a trend in this plot is because the slope of this curve should be negative and the magnitude of it should be equal to the entropy. So this is just a general trend one can expect when a single component system is experiencing a change with change in temperature while the pressure is assumed to be constant. So this is a generalized trend, and it is critical for us to note that it has a negative slope. So let me, in order to highlight the differences or the key points, let me use a different color. So it has a negative slope, 1, and secondly, as the temperature. So what we see here is, so the slope of the curve is negative, and the magnitude of it is rather the magnitude of it, it indicates the entropy. So magnitude of this change in the state, or the change in the Gibbs free energy with respect to temperature, it indicates the entropy. Now when you consider the second derivative of the change in the Gibbs free energy with respect to temperature, meaning the second derivative of the Gibbs free energy with respect to temperature, this would be equal to minus of the change in the entropy with respect to temperature, and this expression rather can be related to one material constant. So that is, if we could recollect, we had this expression, that is, the entropy can be expressed as the change in the, or heat exchange with respect to or for a given temperature. So this is the initial description of the expression of the entropy that we initially attributed. So the entropy is nothing but the ratio of the heat exchange at a given temperature. Now this heat exchange can be related to, rather this heat exchange here can be related to the material property through the heat capacity at constant temperature by considering a specific temperature. So this ratio here, using this ratio here, it is possible for us to describe the or relate the heat exchange to a material property. And when we do that, what we end up having is, so this here is dT and Cp dt will be the heat exchange. So ultimately what we end up having is, when we consider the second derivative, it will be minus Cp by T. So in case of the second derivative of this particular curve here, it is possible for us to relate it to a specific material property or a specific property of the system. Now the reason we need to consider the second derivative of the given thermodynamic function is because while the first derivative numerically gives you the slope, the second derivative, it talks about the curvature. So the curvature numerically is nothing but, you can treat this curve here as a part of a large circle and 1 by r. So this again, this curve can be treated as a part of a large circle, and if you consider the radius of the large circle as r, 1 by r gives you the curvature. Now the second derivative of the expression of this curve here gives you is equivalent to that of the curvature. So numerically, like the first derivative gives you the slope of the curve, the second derivative gives you the curvature. Now since the curvature is inversely proportional to the temperature, so therefore as the temperature increases, the curvature decreases. So we have arrived at, or there it is possible for us to make three distinct observations from this curve, from this schematic illustration. One is the curve, or the curve of the representing the change in the Gibbs free energy with respect to temperature for a single component system is negative, magnitude of the slope. So the slope of the curve representing a single component system is negative, the magnitude of the slope is equal to the entropy, and thirdly the curvature of the slope, it decreases as the temperature increases. So as the temperature increases, since the temperature is in the denominator, it increases as, or rather as the temperature increases, the overall curvature decreases. So this curve is not rather a straight line, but it tends to get more and more curved as the temperature increases. So therefore we will not be having a constant slope, but we will be having a varying slope. So just from this expression and our understanding of the, from our understanding of how the relations between, or how the Gibbs free energy can be related to that of the entropy, we are able to arrive at certain relation or certain characteristic observation of how this change in the Gibbs free energy curve with respect to temperature changes. Now, in addition to this observation here, it is again possible for us to note that this curve is dependent on the material, meaning it is dependent on the material property. So given the state of the material, there will be different curves that you would observe. So primarily because when you have a given material in two different states, since these two different states might possess different material properties, since these two different states often possess two different material properties, two different, particularly the heat capacity, then in that case what we essentially have is, even though we are considering a single system, but in its two different states, given the material property, particularly the heat capacity will be different, what we will end up having is two different Gibbs free energy versus temperature curve. So what have we considered? So what are the characteristic features of the Gibbs free energy and the temperature curve, apart from the negative slope that is indicative of the entropy, and the nature of the slope that can be rather understood by the trend of the slope that can be rather understood by considering its curvature, the other takeaway point that we get from looking into this representation, the schematic representation of the change in the Gibbs free energy with respect to a temperature for a single component system is when there is a change in the heat capacity. When there is a difference in the heat capacity, it means you will be having different plots to represent the change in the Gibbs free energy with respect to temperature. Even though you are considering a same material but in two different states, say for instance water as a solid or as an ice cube and as a liquid water, even though it comprises of the same individual component, the same single component H2O molecule, since the ice cube and water has two different heat capacities, we would be having two different Gibbs free energy versus temperature curve. That is primarily because the curvature of this curve depends on the heat capacity. And there is also another point why there will be a difference in we should expect a difference in the two plots when we are considering a given material in two different states. We will look into in few minutes or in the next lecture. Now, having considered or having understood why there should be two different Gibbs Gibbs free energy versus temperature curve for a given material in two different states, let us consider how such a Gibbs free energy versus temperature curve looks like. So let us go back to our initial example wherein we were considering the solidification, which is rather nothing but a technical way of talking or expressing freezing of water. So in this case you have a single component system but in two different states. So we will consider water and ice cube. So when we consider that, since both these have two distinct properties, two distinct features, particularly the heat capacity, correspondingly your curvature of the Gibbs free energy versus temperature plot would vary. So therefore when you express the solid curve, so if we express the solid curve in line, or the change or the curve that represents the change in the Gibbs free energy of the ice cube with respect to temperature in red, the change in the liquid water or the Gibbs free energy of the liquid water with respect to temperature, we can represent it in blue. So we have looked into the change in the Gibbs free energy with respect to temperature for a single component material in a single state. Now we are extending that assumption to single component material. We are holding the material but we are considering two different states. Now the reason we have two different curves is because these two have two different properties, particularly the heat capacity, and the heat capacity becomes dominant. The role of the heat capacity becomes dominant as the temperature increases. So that is one of the key observations that we saw in our previous discussion. As the temperature increases, the curvature of the curvature correspondingly decreases. So there is a characteristic association. Between the between the nature of the curve and the property of the material. So as the temperature increases, what we essentially see a corresponding change in the nature of the curve. So therefore we have two characteristically different Gibbs free energy versus temperature plot for the solid and for the liquid. Now we saw, while considering or while introducing the Gibbs free energy, we saw that the Gibbs free energy for a spontaneous change, the Gibbs free energy should be negative. The change in the Gibbs free energy, that is delta G, should be negative because the delta G in its canonical form is expressed in this way, and here we have a constant increase in the entropy, and when you have a constant increase in the entropy, particularly as the temperature increases, the role of this term keeps on increasing. The importance of this term keeps on increasing, particularly as the temperature increases, and as for irreversible change, the delta S is always increasing. That is the criteria that we observe from the second law of thermodynamics. So ultimately, when this term keeps on increasing, for a spontaneous or an irreversible change, the delta G should be negative. And the same can be observed, or the same can be understood from this expression here, that is, for a spontaneous change, the delta G should be negative. So again, from this expression, since entropy is preceded by a negative sign and the entropy is positive, 0 and above, and it is always increasing, so the delta G as, or a change in the Gibbs free energy, should decrease for a irreversible change. Or to put it another way, we saw that when you have a change in the Gibbs free energy with respect to another variable, the stable state of the particular system is when the Gibbs free energy is at its minima. So whenever you have whenever you are comparing different states of the system for a given condition, the stable state is often associated with the one wherein the Gibbs free energy is at its minima. Now in this case, except for this point here, for each of the other temperature, we have two different Gibbs free energies. So we have specific Gibbs free energies for the solid, and we have corresponding Gibbs free energy for the liquid for each temperature that we have considered. For every temperature that we have considered, we have rather Gibbs free energy of the solid and the Gibbs free energy of the liquid. Now below this particular temperature, below this point here, the Gibbs free energy of the solid is less than that of the Gibbs free energy of the liquid. So therefore the solid below this point here is stable. So let me use black. The solid below this point here is stable. So below this point here, it is solid that is stable. However, when you move away from this point, the Gibbs free energy of the liquid is less than the Gibbs free energy or the solid. So therefore it is the liquid that is stable beyond this point. So what essentially we have captured here is, we have captured the melting point, and below the melting point it is the solid that is stable, and above the melting point it is the liquid that is stable. And this we are able to identify, or this we are able to realize from the Gibbs free energy versus temperature plot. So in order to understand that, we need to have certain understanding of how Gibbs free energy changes for an irreversible process. So the irreversible or a spontaneous process, it means that the system is moving towards a stable state, and when the system is moving towards a stable state and the Gibbs free energy of the system is decreasing, it means at the stable state the Gibbs free energy is at its minima. Now for every temperature here, for instance, if we are considering this temperature here, so if we are considering a temperature here, say T1, the Gibbs free energy of the liquid is this at T1, and the Gibbs free energy of the solid is this. So we have a noticeable difference between the Gibbs free energies. So the delta G here will be the Gibbs free energy of the solid minus Gibbs free energy of the liquid, which will be negative because this condition is satisfied. So this will rather dictate the irreversible process, or this will rather dictate the solidification or freezing below the melting point. So what we essentially have is, it is possible for us to describe the thermodynamic driving force for a freezing or solidification using the difference in the Gibbs free energy. So all that we have done is, we have considered a simple Gibbs free energy equation. We have assumed the pressure is constant, and we are left with this expression here, and we just considered single component system in its initial state, a single state, and we plot the Gibbs free energy versus temperature, and we observe that there is a characteristic properties associated with it, and from that characteristic property we were able to consider two different states of the single component system. And when we consider these two different states, now we are able to state which state will be stable at which temperature. So based on whatever understanding we gained from a single state, single component system, so this schematic representation here, whatever understanding we were able to gain from this, based on that we were able, or we are in a position now to state which phase will be stable for which temperature. And we were also able to identify at which temperature both these phases will be stable with one another. So at which temperature can we observe both these phases. So both these states, that is both solid and liquid, at which temperature can be observed. So what essentially this discussion helps us do is, thermodynamically it now has become possible to discuss the driving force for the change in the state of the system through the Gibbs free energy, and how much driving force through this plot here. So this is the first step towards identifying which state or which phase, solid or liquid phase in this case, would be stable at a given temperature. So we will build on this understanding, and we will see what more we can gain from this representation or this discussion on which phase will be, or which state will be stable at a given condition. Goodbye.